So conductors are very good at allowing charged particles to move around them freely. Copper is a really good conductor, just like other metals. And the reason why copper and other metals are good conductors is really because of the electron configuration. Copper has this one electron that is a valence electron, and it's really far away from the nucleus. It's also kind of shielded by all of these other electrons. So this outer electron is very loosely bound to this atom, and that means it's really easy to remove. So if I put a bunch of charges on a conductor, those charges are able to kind of bounce around from one copper atom to the next, and they will move as far away from each other as they can because of the repelling Coulomb force. And so whenever you have charge on a conductor, that charge will move away to as far apart as possible, which means the charge will always collect on the surface of the conductor. So one thing you can kind of memorize is that whenever you have a conductor and there is some net charge on it, that net charge will always go to the surface. And that means there's no net charge inside this conductor, inside this inner area. All the charge stays out on the outside of the conductor. We see something really interesting with conductors that don't have any net charge on them, so a neutral conductor. If we take that and we put it in an electric field, we're going to see something really interesting. So here I have an electric field, and then I'm going to take, let's say, a square piece of copper, and I put it in that electric field. Because the valence electron in every copper atom is so loosely bound to the nucleus, it's really easy to move. And so this external electric field can provide a force on those electrons and move them. And since this electric field is pointing to the right, electrons will feel a force to the left. And when you move a bunch of those electrons to the left, we're going to have positive charge remain in its place. We're going to have an equal amount of negative charge and positive charge on either end of this conductor. Because remember, this conductor is electrically neutral, but because it's made out of copper atoms, the electrons can move very easily in this conductor, and that external electric field separated out this charge. So now we have a conductor that is polarized. When you have this separation of charge, we can have an electric field produced in between that separation of charge. So we know electric fields flow away from positive charge and towards negative charge. And so this electric field I've drawn here, I'm calling the internal electric field. This is the electric field that develops between the negative charge and positive charge that was separated in this conductor. But this system reaches an equilibrium so that the internal electric field is actually equal in magnitude to the external electric field that produced it in the first place. So what we have here are equal electric field magnitudes, but they point in opposite directions. So what's the net result? A zero electric field inside this conducting slab. What we have when we put a conductor in an external electric field is zero net electric field within that conducting material.